We will continue our molecular geometry. We were drawing pH3. We said phosphorus, who lives in group 5A, would have 5 valence electrons, and each of the hydrogen has 1. There's 3 of them, so we have a total of 8 hydrogens. We also mentioned that we should never select hydrogen to be in the center. It's always attached back to the central atom or even further out yet. That means phosphorus is going to be placed in the center. We attach the hydrogens back to the central atom, and to do that we used 2, 4, 6 electrons, leaving us a remainder of 2. Now those extra 2 electrons will not get placed on the outermost electron or the outermost hydrogen atoms because they are already satisfied their octet by becoming helium. So remember, hydrogen only get 2 electrons. So the remaining 2 get placed on the phosphorus itself, the central atom. So here we have a central atom of phosphorus with 3 bonded hydrogens and 1 lone pair. There's 4 domains. 1, 2, 3, 4. Of the 4 domains, 3 are bonded and 1 is not bonded. So on our VSEPR chart, we come and we find 4 electron domains, 3 of which are bonded and 1 is non-bonded. It's called a trigonal pyramid. The domain, of course, is still tetrahedral. There's 4 domains. An example is pH3. With 4 domains, SP3 is our 4 fingers, S, P1, P2, P3 for 4 domains, and the bond angle is, well, it'll be a little less than 109.5 because of the lone pair pushing those hydrogens enter. So let's draw it. Phosphorus in the center, and again, think about trying your best to draw what this is here in terms of, that's the wrong one, in terms of the geometry. We're trying to draw a trigonal pyramidal, so we have this lone pair of electrons and 3 kind of pointing down. So we'll draw 1 lone pair, point down is a hydrogen, point down is the hydrogen, point down is the hydrogen. And we can see that the bond angle here, if I wanted to label and just keep the red here, would be just slightly less than 109.5. Simply because those lone pair of electrons, remember this highly electron cloud region there is pushing those hydrogens closer together. So the electron domain here of 4, 3, 0, 4 domains, 3 of them bonded, 1 of them unbonded, 3 and 1 equals 4, gives us a molecular geometry of trigonal pyramidal. With 4 domains, it is a tetrahedral, 1, 2, 3, 4 electron domain. This molecule is polar. The area up here would be partially negative, and each of those hydrogens would remain partially positive. The electron density is getting pulled toward the top of the phosphorus. The bond angles we said would be slightly less than 109.5, and it has sp3 hybridization. Let's consider number 4, which is arsenic pentafluoride, ASF5. We'll go to scrap paper first. Let's tally up how many electrons we get in ASF5. Arsenic, who is AS, lives in group 5, so it will be donating 5 electrons to the molecule. And fluorine lives in group 7, and there's 5 of them there. So here we have 35 electrons for a total of 40 electrons by the time we're done creating our molecule. Arsenic gets placed in the center. It's the one we have just 1 of. It's the least electronegative, and we have to attach back all of the other atoms to the central atom. And notice there's 5 of them, so this means we have to expand the octet. We're going to have a rule breaker here. it's going to have more than 8 electrons around the center. So just kind of roughly putting them here, I'll have 1, 2, 3, 4, 5 fluorines attaching back to the central atom. 2, 4, 6, 8, 10 electrons were used, leaving us a remainder of 30 electrons. Then the rules say, with those 30 electrons, fill the octet of all of the outermost electrons, which are the fluorines. So we'll need to place 6 electrons around each of those fluorines to satisfy its octet. How many did we use? Well, we placed 6 around each of those 5, so we used 30 electrons, giving us a remainder of 0. We've actually just created a molecule that has formal charge, all of 0. Arsenic, who lives in group 5A, even if we expanded its octet, it has 5 valence electrons assigned to it, lives in group 5A, the formal charge is a 0. And each of these fluorines, who live in group 7, also are assigned 7 electrons, have a formal charge of 0. This is the ideal structure, eliminating any formal charge by expanding the octet of arsenic pentafluoride. So we had 5 domains, all 5 were bonded, 0 were unbonded. On the VSEPR chart, we need to find the 5, 5, 0. 5 total domains, all 5 were bonded, 0 were unbonded. It's now going to have a molecular shape of trigonal bipyramidal, which is also the electron geometry, trigonal bipyramidal, and there's our molecule ASF5. There's 5 domains, so S, P1, P2, P3, D1. There are only 3 p sublevels, right? 3 orbitals in the p, so S, P, D1 are the 5 domains, sp3d. And when you build this, it will literally have 2 different types of bond angles involved. You'll see that here is an equilateral triangle going around the central atom. Can you see that triangle there? These are 120 degrees around that equatorial position there. This is like the equator. And these axial positions come up and come down. They're like the flagpole positions, straight up, straight down. So you see the 90 degrees or 180 degrees from top to bottom. 90 degrees here. And when you build this, you will see that it literally has 2 different angles. So let's transfer that, and knowing that we have to do our best to actually draw this structure for ASF5. Arsenic goes in the center. One of the fluorines straight up, one of the fluorines straight down. Then we have to build an equilateral triangle around the equatorial positions. So that's how I'll do that. We have a bond angle here of 90 degrees, but between all of those around the center arsenic going around in this circle, these are all 120. So those are all 120 degrees. Alrighty. We said that there were 5 domains, all 5 bonded, 0 unbonded. The name of this is called trigonal, and that's because this is an equilateral triangle. 1, 2, 3, the face of an equilateral triangle. And then the other word is bipyramid, or bipyramidal. Electron domain geometry is the same because all of the atoms are bonded back to the central, no lone electrons. This is a nonpolar molecule, completely symmetrical. 2 different bond angles we have drawn in, 90 and 120, and an sp3d1 hybridization. And one last compound we're being asked to draw. SeCl6, selenium hexachloride, SeCl6. And again, I'm trying to select some from each part of the VSEPR chart. SeCl6. So some scrap paper. Let's figure this out. Selenium, find my periodic table, Se selenium lives here in group 6. So it has 6 valence electrons. And we're attaching back to that chlorine, which has 7 valence electrons. The least electronegative, the one that we have just one of, will be selenium. It will serve as our central atom, and we need to attach all those chlorines back. So you can see we're going to expand the octet in our last example as well, pulling from a 6 domain. So we said selenium with 6 electrons, chlorine who has 7 electrons, but there's 6 of them there, so that's 42 electrons that chlorine will, each of those will donate. Total number of dots we have to place are 48 electrons. Attach all of those chlorines using a single bond and subtract what we've just used. 2, 4, 6, 8, 10, 12, leaving us with 36 electrons to place. With those, our job next is to fill the octet of all of the outer electrons. So each of those chlorines will need 6 dots placed around it. And when we do that, how many did we use? Well, each of those 6 had 6 dots, so we used all 36, so there's none left to place on the central atom. If there are remaining dots, that's where they go next, is on the central atom. So this is our rough draft. We have 6 electron domains. All 6 are bonded, none are unbonded. With the VSEPR chart, we need to find the 6 domains, all 6 bonded, none are unbonded. It's going to look like an octahedral structure, both for electrons and the molecular shape. 6 domains says S, P1, P2, P3, D1, D2 gives us 6 domains, and it will literally look like 90 degrees. So I've tried to draw a rough draft there. Let's transfer it. You'll have a chlorine straight up, straight down, and then literally a box around the central equatorial positions. These are known as the axial positions around the center, or the equatorial positions. Place all those dots around there. My goodness, I forgot up here too. That would lose me points. We got a lot of dots to fill in, and I'll do so quickly. Please make sure you did the same. Same thing for the chlorine. I have to have the same number of dots as we were instructed to place based on counting valence electrons. There we go. And each direction, it doesn't matter where, they're always 90 degrees. Any between there, you'll find that they're 90 degrees. So we had 6 domains, all 6 were bonded, 0 unbonded. It was called an octahedral. Same because we had no unbonded pair, making this nonpolar, and sp3d2 hybridization, sp3d2. Now I selected one from each position. You're going to be building 20 electron structures, and I bet you'll have a variety of different electron domains and molecular geometries. This is the pattern that we'll follow for all 20 structures. The other part of the directions say as you're building these, this would be like a pH3, here is your carbon dioxide. As you're actually building these from your molecular models, you're instructed to have your instructor, your lab instructor or the lab aide, check these before you disassemble them. We want to be sure that you're actually seeing the structures and not just putting them on two-dimensional paper. So every time you build a few, call us over and we'll check them off before you tear them back down. Great, I look forward to seeing you in lab.